Hi guys, so we are going to continue with our notes. We are now on sketch notes number 5. Number 4 should have been the planet storybots. So we are moving on to the atom. So you're going to title the sketch notes the atom. So by now you should remember how to get to the notes if you ever want to go back to it, but they are on our website and there's a link. So remember, anything that is underlined has a link to it. So sketch notes number 5, the atom. So the atom is made up of 3 subatomic particles. We've already talked about this several days now. We watched it in the storybots. We did it with the last notes. It's made up of electrons, protons, and neutrons. Remember, the protons are positive, electrons are negative, and neutrons are neutral. The protons and neutrons are they're bigger, so they are what would make up the mass of the element, where the electrons, they're so light that they don't actually count as the mass. And I want to show you a picture because it's really hard to draw a picture of an atom because electrons are actually moving so fast around the nucleus of the atom that you can't even see them. There's no one particular place that they're ever in at any time. They're just moving super fast. So here's a picture of what the electron cloud looks like.
Good to see you. Yeah, hey, what's with the polka dots? What do you mean? Polka dots are out. It's focus.
The electron does not orbit the nucleus. We cannot know the path of the electron, as stated by Heisenberg in his uncertainty principle. We do know, however, that the electron travels very quickly within a defined space, creating a cloud of negative charge. For further information, please click here to see my orbitals video.
Okay, so that was a video of what the electron cloud looks like. All right, nomenclature. So the number of protons in a nucleus. Oops.
What is the electron?
Sorry about that. I need to close that. All right, let's try that again. All right, so the number of protons in a nucleus is the atomic number. So this is no matter what, that never changes for that particular element. So if you have 1 proton, you will always have a hydrogen atom. It doesn't matter how many neutrons or how many electrons even there are. Electrons are usually, for a stable atom, we want to have the same amount of negatives as we have positives. So usually, for our sake at this level, for 8th grade level rather, we are going to say that we have the same amount of electrons as we have protons because we need to have the same amount of negatives as we have positives. Neutrons are a completely different story. We could actually have less or more than we have protons or electrons. So if you see here for hydrogen, well, I'm getting a little ahead of myself, so let me read the next sentence. The atomic mass is the number of protons plus the number of neutrons. So to find the atomic mass, or to find the number of neutrons rather, because neutrons isn't straight out given to you, we have to do a little bit of math. So what we would do is we would take this mass number and subtract the number of protons from it. So this is our atomic mass down here. These numbers down here at the bottom, those are the bigger numbers. And remember, when we were making our nameplates, I had you guys look those numbers up, and I told you that we would go over what they mean. So this is the mass of the atoms. And I'm going to explain in a little while why there's a decimal there, but we are going to find the number of neutrons, we're going to round it first. So for this one, hydrogen, we would round it to number 1. And 1 minus 1 would be 0. That means usually in a sample of hydrogen, for the almost 100% of the time, we're going to have no neutrons. Sometimes, though, there's actually 1 neutron, 2 neutrons, or 3 neutrons. So sometimes there are more neutrons, but usually there are no neutrons. And that's rare. This is the only element that there are no neutrons. Uranium, on the other hand, you would subtract 238 minus 92, and you would find the number of neutrons for uranium, which would be more than 92. So there would be usually a lot of the elements, it's either double the number of protons or it would be greater than the number of protons. All right, so I'm going to give you guys a little time to try to answer these questions on your own. So what do the numbers mean? What element is this? So I want you to look at the picture, read, look around, see if you can label, identify what name of the element there is. What is the mass of this element? How many protons are in this element? Calculate, again, rounding, you're going to calculate how many neutrons are in this element. And then on a stable element, how many electrons would there be? You guys did learn about the electrons, that the electrons aren't always present, because remember when we learned how electricity flows, sometimes electrons go from atom to atom, so they're constantly moving. They can move from atom to atom. So in a stable element, or in a stable atom, we're going to say that electrons are the same number as protons, but we will learn about isotopes and ions and how things are different for other, so how electrons and neutrons change for some atoms. So protons are always 100% the same. Neutrons and electrons aren't necessarily the same. But for 8th grade, remember, if I ask you how many electrons are, it's the same as the number of protons. So now let's go through these questions and see if you got them right. So what element is this? Here's my name. The name is lithium. What is the mass? So the mass would be the big number down here, 6.941. How many protons are there? Protons are up here, so 3. How many neutrons are there? Remember I said to round. So we would round this up to 7 to make 7 our whole number. And then we would do 7 minus 3. So our answer for neutrons would be 4. And I said it's usually about double the atomic number or the number of protons. And then for a stable element, we would also have 3 electrons. So 3 protons, 3 pluses, 3 electrons, 3 negatives. So they cancel each other out. They have a neutral charge. All right, so isotopes. So this is what I was just saying with before on the last slide. So if you, as you've seen, atoms of the same element can have different numbers of neutrons. So carbon, for example, we use carbon a lot. If you remember from 7th grade, carbon is found in all living things. So this is actually how we're able to identify how old fossils are. We're going to be doing a little experiment with that, a little simulation with that in a couple of days. So for example, some carbon atoms have 6 neutrons, some carbon atoms have 8 neutrons. So the number here, let me read this last sentence, sorry. So atoms of the same element have differing numbers of neutrons are called isotopes. So when we have different amount of neutrons, they are called isotopes. And this is the number, this is our mass. So for carbon-12, it's saying that we have 6 protons and 6 neutrons. So remember, the only thing that makes up the mass is the protons plus the neutrons. So this is where our carbon-12 comes from. For this carbon-14, we have 6 protons and 8 neutrons. So 6 plus 8 is 14. So that's where that number comes from. And again, the electrons are so small. They weigh almost nothing. Well, they all kind of weigh almost nothing, but they're so tiny, they don't make a difference in the mass. So it's kind of like if you step on the scale and you weigh 100 pounds, and then you step off and you pluck off a piece of hair and you get back on the scale. Your weight isn't going to change. Your hair will not change the weight that you are. So that's kind of where electrons are. So isotopes of an element will always have the same number of protons. It's hard to see this with all these pop-ups down here, but differing masses because they have different numbers of neutrons. So up here, you notice same number of protons. That means we're still talking about carbon. So if the proton changed, we won't be talking about carbon anymore. If this became a 7, now we're into nitrogen and not carbon anymore. All right, so this was, I think we were supposed to do a little math here, but you can see that neon 20 is 10 protons and 10 neutrons, so that's where our 20 comes from. Neon 21 is 10 protons and 11 neutrons, so 10 plus 11 is 21. And then neon 22 is 10 plus 12, which is 22. Again, the electrons are canceling out the charges of the protons, so they don't count in the mass. All right, so isotopes and atomic masses. So this is why we have a decimal, because if you learn from math, you should have learned by now, you've been learning it at least since 5th grade, probably even before, to find the average of a number, you add up all the numbers and then divide by how many you have. When we're talking about atoms, they're so small and you have so many in a sample, what we do is we take a percentage of how many, for example, neon 20s. So neon in the world, in a normal sample of neon, we would normally find 90.48% of neon 20. We would normally find 0.27% of neon 21. And we would normally find 9.25% of neon 22. So in a 10,000 atom sample of neon, I'm just going to shrink this down so we can see what it says. You would multiply 10,000 times 90.48%. So remember, you have to move the decimal over 2 places. So it would be 0.9048 times 10,000, and you would get 9,048. Same thing, you would multiply 0.27. So now we have to move the decimal over 2 places. So it would actually be 0.0027 times 10,000. And for the 9.25%, we would move it over 2 places. So we'd have 0.925 times 10,000. And these are the numbers. So then...
Daddy's here, so we can buy his wizard box.
Okay, let me finish this up. All right, so this is how we would find the atomic masses of the isotope. So in 10,000, 9,048 of them are neon 20. 27 of them are neon 21, and 925 of them are neon 22. And when you find the average of that, that's where that decimal would come in. So atomic mass is a weighted average, which is why we're not going to count. We're not going to put in 10,000 numbers, obviously, when we're trying to do mass. Oops. I need to present, sorry. All right, so there's a difference between the atomic mass and the mass number. So the atomic masses, those are the numbers that are the decimals that are given to us usually with the periodic table. So the atomic mass is the average of all the atoms' masses in a sample. It's going to be a decimal form. Where the mass number is if I was talking about a particular atom or a particular isotope of that atom. So that would make it a whole number. So if we went back to the neon here, so this would be the mass number would be 20 for this particular one because we're adding 10 plus 10. For this would be the mass number. But neon, as it's on its own, let me just look that up really quick. Neon's atomic mass is 20.1797 or 20.18. So depending on which one you look at, where they rounded. All right, so just to make that a little bit more clear so that we understand it a little bit better, when we're talking about atomic mass versus mass number, usually we're going to talk about atomic mass. That's the one that we are going to use most of the time. It is like saying in this diamond, there are multiple versions of carbon. Diamonds are made up of carbon, and the mass, the average of all of the atoms that make up this diamond is 12.01. However, for this particular one atom, if I pulled one of these atoms out and I put it over here, this would be my mass number. So my mass number, when I add up my protons plus my neutrons, this would give me carbon 14. All right, so it's, to calculate, this is just going back to the neon again. To calculate, we already talked about this. You would multiply each, no, I guess I have to exit to be able to show you guys everything, sorry. So you would multiply each of the neon 20, the neon 21, and the neon 22 by the percentages. So before I showed you how to find how many of the atoms were in a 10,000 sample, sample. This is to calculate the actual percentage or the actual average. So you would take your percentage again, turn it into a decimal. So move the decimal over 2 places, 0.9048, and you would multiply that by your each one. So that goes with the neon 20. The 0.0027 goes with neon 21. 0.0925 goes with neon 22. When you multiply them, then you add the three numbers together, and that's where the 20.18, which is what we just looked up, and AMU is atomic mass number, that's where that average comes from. So it's very easy to calculate it. You just find the percentage of each isotope, get what that percentage equals, and then you add them all up, and that's your average.
Oh. When is it going to be my birthday?
So again, if you're unsure about that, you can re-watch what I was saying, or you could always ask me in class to go over it to make it a little bit more clear.
I love it.
All right, so atomic mass unit, AMU, capital, all capitals or all lowercase, that is how we measure the atoms, the atomic mass. All right, so I want you guys to try this one on your own. You're going to calculate the atomic mass. So if we have carbon, it consists of 2 isotopes for this example. So this is a picture of coal. Coal is also made up of carbon. So we have carbon 12 and carbon 13. So if 98.89% of all carbon is carbon 12, first we need to turn that into a decimal. And then we need to figure out what's left to make 100%, turn that into a decimal, and then you would multiply the percentage, the decimal, by this one, it goes with the 12, and what you calculated for the 13. And this is what you should have gotten. So the remainder to get to 100% or to get to 1, if we already change it to a decimal, is 0.0111. If you move the decimal over, that would be 1.11%. When we multiply it together, we have 11.8668 AMU and 0.1443 AMU, which would equal our 12.0111 AMU. Okay, so here's another example that I want you to try. So this is for copper. So an element of copper, naturally occurring isotopes with a mass number 63 and 65. So the relative abundance for the atomic masses are 69.2 for a mass of 62.93 AMU and 30.8% for a mass of 64.93 AMU. So I want you to calculate the average atomic mass of copper. I'm going to give you a few seconds to try to figure this out on your own. Okay, if you haven't figured it out, just pause the video and then come back when you're ready to check your answer. Oops. Oh, I didn't type it up. So now I actually have to get a calculator. All right, so I'm just going to tell you how to do it. So you would actually take these would not matter. You don't need to use this AMU. You would actually take your percentage and multiply it with the isotope. So the relative abundance and atomic masses are 69.2%. So that would be multiplied with the 63 AMU. And the 30.8%, you would multiply it with the 65. And then when you get your answer, you would add those two together, and then you would get the average atomic mass of copper. And I don't have a calculator available right now to tell you an actual answer, so we'll have to do it in class or if you ask. All right, so now this, we don't actually have to do any math. We just have to read and try to figure out the answer. So this is why isotopes are important in the real world. And this is, I think, the last slide that we need to do for this. So application of isotopes. All right, so elephants are hunted for their ivory in their tusks. Game wardens use isotopes to track where elephants are going so they can help protect them. If an elephant eats a plant from a wet climate, the ratio of N15 to N14 in their hair will be lower. So that means there would be less N15 to N14. So there would be a smaller number of N15 than there would be N14. Than typically found in nature. If they graze plants grown in a dry climate, they will have a higher ratio of N15 to N14. So N15 would be a bigger number than N14. So where would you look for an elephant? So we're looking for wet or dry that had a hair sample with a ratio of 0.0045 for N15 to N14. But the normal ratio is 0.0034 N15 to N14. So I'm going to give you a little bit of time to think about that. All right. And if you said a dry climate, then you are correct. Because let me just go back, 0.0045 is larger than 0.0034. And we said over here that the N15, we would have a higher ratio or a larger number than normal if for a dry climate. So just a little real world application there. Okay, we are not going to take a pop quiz, so don't worry about that. So we are going to stop our sketch notes right here. And make sure if you had any questions that you ask me in class. Maybe put stars next to any questions so you can remember to ask me in class if you have any questions.
No,